back to the deep dive. Today we are undertaking, well, what might be the most ambitious analysis we've ever attempted.
I think you could safely say the most ambitious.
We are diving into the single biggest, most vexing problem in all of modern physics.
The century-old schism.
Exactly. The one that tears at the very foundations of reality. We're talking about the failure to unite general relativity and quantum mechanics.
It's the ultimate theoretical open wound. And our inability to bridge this gap has defined high-energy physics for the past 50 years.
It's so strange when you think about it, because the history of physics is really a history of unification, right?
It is. It's defined by these great acts of unification. You think of Newton, who showed that the laws making an apple fall are the exact same laws that keep the moon in orbit.
Or Maxwell.
Maxwell, who wove together electricity and magnetism and showed they were just two faces of light. And then, of course, Einstein fused space and time, and then energy and mass.
Each of those unifications gave us this massive, almost unimaginable leap forward in how we see the cosmos. But then we hit this wall.
This absolute brick wall, gravity.
The quantum world and the gravitational world just refuse to share the same mathematical stage.
They really do. You've got general relativity, GR, which is Einstein's masterpiece, and it describes space-time as this smooth, continuous, warping, dynamical fabric. It's a theory of geometry, fundamentally.
Yeah.
A description of a continuous curve.
And on the other side,
you have quantum mechanics, QM, and it describes a world that is fundamentally discrete. It's all about probabilistic leaps, inherent uncertainty, and, well, quantized values. It just does not tolerate continuity.
So the moment you try to apply the rules of one to the other,
the calculation becomes completely nonsensical. You try to quantize the geometry of space-time itself, and the whole thing just falls apart.
So if I'm following, they're basically speaking two different languages about the same fundamental thing. Where does this incompatibility become a catastrophic failure?
It happens at the most fundamental level you can even imagine, which is the Planck scale.
That's, what, 10 to the minus 35 meters?
Roughly, yes, and almost inconceivably small length. At that distance, the smooth, predictable curvature of space-time that GR relies on, it just dissolves.
It dissolves into what?
Into a violent, foamy chaos of quantum fluctuations. It's often called space-time foam. All that smoothness is gone.
And when we try to use our normal mathematical tools like perturbative quantum field theory to describe gravity at that scale, what happens?
We get those famous catastrophic ultraviolet divergences, the methods that work perfectly for the other three forces, electromagnetism, the strong and weak nuclear forces, they just yield nonsense.
Not just a wrong answer, but
literally nonsensical infinities. They tell you the probability of anything happening at that scale is infinite, which is just another way of saying your theory is fundamentally non-predictive and completely broken.
So a foundational incompatibility between continuity and discreteness. And the stakes here are just incredibly high. Because this isn't just about cleaning up some math, right? It's about the fundamental nature of reality itself.
Precisely. Is space continuous, or is it made of discrete little pieces? That's the question. And this failure has fractured the theoretical physics community for 40 years.
Leading to the two big adversarial contenders we're diving into today.
On one side, you have string theory. And it's based on, well, let's call it infinite ambition.
The theory that promises to be the theory of everything.
Yes. String theory posits that the fundamental constituents of the universe, quarks, electrons, gravitons, everything, are not zero-dimensional point particles. Instead, they're tiny, one-dimensional vibrating strings.
And its goal is total unification.
Total. Pulling all four forces and all matter into one single mathematical object. But, and this is the big but, to achieve that consistency, it demands a dramatic expansion of our reality.
Extra dimensions.
We need 10 or 11 dimensions in total for the math to work.
And then, opposing that behemoth, we have what you've called the minimalist, the purist approach.
That's loop quantum gravity, or LQG. And LQG completely rejects the fixed background that string theory needs to operate.
It claims to be the true inheritor of Einstein's legacy.
It does. Its entire mission is to focus strictly on quantizing the geometry of space-time itself to really honor Einstein's core idea of background independence.
Its picture of the universe is radically different.
Radically. It predicts a universe that is fundamentally granular. Space is woven from discrete little pieces called spin networks. LQG is much humbler in its scope. It promises no extra dimensions, no new particles.
It just promises a consistent quantum description of the geometry we already know.
That's the goal.
Okay, let's unpack this. Both of these theories seem conceptually rigid. They define success in totally different ways and, both are plagued by these deep technical stalemates as of 2025. We have to start with string theory, the heaviest lift, with the massive weight of its infinite ambition. It's still one of the most surprising facts in physics that string theory didn't start out trying to describe gravity at all.
That's absolutely right. I mean, its origins back in the late 60s were purely focused on describing the strong nuclear force, the very messy dynamics of quarks and gluons.
And it didn't work for that, right?
It failed in that original domain, yeah. It predicted a whole array of particles that just weren't observed in strong interactions. But then came this stunning realization.
The graviton.
That its mathematical spectrum inevitably contained one very special particle. A particle with 0 mass and a spin of 2. And, well, no other known force particle fit that description.
It had to be the graviton, the quantum particle that mediates gravity.
It had to be. It was like this theoretical gift, an accidental unification that just came pre-packaged with the theory.
And it immediately solved that core catastrophic problem we talked about, the infinities from point particles.
It did. The central premise that saves string theory is that the strings smear the interaction vertex in spacetime. So instead of two zero-dimensional points colliding, which is what causes those divergences,
you have two extended loops interacting over a small volume.
Exactly. And that smearing successfully removes the infinities. Mathematically, it's just beautiful.
But as we mentioned, that mathematical consistency comes at a very steep price, extra dimensions. Why? Why does the string theory engine demand 10 or 11 dimensions to run properly?
It's a purely internal demand from the mathematics. The underlying equations of string propagation, specifically the requirement that the theory has to be free of quantum anomalies and ghost states particles with negative probability.
Which would be unphysical.
Completely unphysical. Those conditions are only met when the theory is formulated in 10 dimensions for superstrings, or 11 dimensions for what's called M theory, which is the sort of umbrella framework for all the string theories.
So it's not something physicists asked for, it's something the maths just forced on them?
It imposed it, yes.
But we, demonstrably live in a four-dimensional world, 3 of space, 1 of time. So to bridge that gap between 10 and 4, string theory needs this concept of compactification.
Correct. The idea is that those 6 or 7 extra dimensions are curled up. They're curled up into these minute, unobservable geometric shapes, way too small to detect. We're talking scales that are possibly near the Planck length itself.
And these shapes are the Calabi manifolds.
That's right, these very specific, very complex geometric shapes.
And this is where the physics of our universe really hangs in the balance, isn't it? Because this specific shape and size of those curled up manifolds, they have to be absolutely fixed.
Absolutely. Otherwise, our physical laws, like the charge of an electron or the strength of gravity, they would be fluctuating constantly.
Which leads to the core of the moduli stabilization problem.
It is the core problem. The size and shape parameters of these hidden dimensions are controlled by scalar fields called moduli. And in a naive, simplified version of the theory, when you go from 10 dimensions down to 4, these moduli fields are massless.
And massless scalar fields are very bad news for our observed universe. Why is that?
They're a phenomenological catastrophe. They lead to 3 major problems all at once. First, if they're massless, they would mediate these long-range fifth forces.
And we've looked for those.
We've looked very, very hard. Experiments testing the equivalence principle, the idea that gravity acts equally on all matter, have strictly ruled out any such forces. Second, since the moduli control the size of the hidden dimensions, they also determine all of our fundamental constants.
The fine structure constant, the electron mass, all of it.
All of it. If the moduli are massless, they would just fluctuate wildly across space and time. The laws of physics would be fundamentally unstable.
So for our universe to be stable, string theory has to find a mechanism to fix these moduli fields, to give them a very large mass and lock them in place.
Precisely. They have to be stabilized in a potential energy well. The first major attempt to do this was through what are called flux compactifications.
So what are fluxes?
You can think of them as higher dimensional analogs of magnetic fields. String theory allows for these generalized fluxes to wrap around the topological cycles, the little loops and holes of the Calabi manifold.
And the energy from these fluxes?
The energy inherent in these fluxes creates a potential energy landscape that effectively locks the shape of the manifold and the string coupling strength into a minimum.
That seems like a really elegant fix, using the theory's own properties. Why was it only a partial solution?
Because the fluxes were great at stabilizing the shape moduli, but they generally failed to stabilize the overall volume moduli.
Aside.
The overall size. The potential for the volume modulus remained flat in the classical theory, and that is a fatal flaw. Without a fixed volume, the extra dimensions could just expand forever or collapse to a point without any energy cost. The whole structure is fragile.
This is where it gets really, really interesting, because this forced what you called a technical Hail Mary, the KKLT mechanism proposed in 2003. This was the first real attempt to get a fully stabilized vacuum.
And it's a theoretical Rube Goldberg machine. It's incredibly complex, but the goal was absolutely critical to achieve a fully stabilized vacuum that also possessed a positive cosmological constant.
What's called de Sitter space.
De Sitter space. This is essential because our universe isn't static and it's not collapsing. It's expanding at an accelerating rate. And that acceleration is described by de Sitter geometry.
And this mechanism has three critical, very delicate stages to get us there.
The first stage is what I call the descent. They start by using those classical fluxes we talked about. They stabilize the shape and the string coupling, but they inherently create a vacuum state where the energy is negative.
Which is anti-de Sitter space, or ADS.
Correct. A hypothetical ADS universe would just collapse in on itself. So they start in this collapsing, unphysical universe.
Okay, so stage 2 is about fixing the volume.
Right. Stage 2, the volume fix. To fix the volume modulus, they need a barrier, and the classical fluxes won't do it. So they introduce quantum effects, specifically non-perturbative corrections like instantons.
Which are like quantum tunneling events.
Exactly. And these effects generate a potential barrier that fixes the volume at a stable, finite size, but still within that negative ADS minimum. It's a bit of quantum magic to fix a classical flaw.
And then finally, they have to lift that negative energy state up into the positive energy state of our accelerating de Sitter universe.
Stage 3, the uplift. This is the most complex and by far the most controversial step. They introduce a localized source of positive energy.
An anti-D3 brane.
An anti-D3 brane, yes. They place it at a highly curved region of the manifold, a warped throat. This anti-brane breaks the remaining supersymmetry and provides just enough of a kick, just enough energy to uplift the vacuum minimum from its negative value to a small positive value.
It's an incredibly clever construct. But you said this solution opened the floodgates to the landscape problem. What did KKLT unintentionally unleash?
The problem came from the details of the flux stabilization itself. The flux that wraps around those topological cycles has to be an integer, like a quantized magnetic field line.
You can have one unit of flux or two, but not 1.5.
Exactly. And since these complex Calabi-Yau manifolds have hundreds of distinct cycles, and you can wrap different integer amounts of flux around each one, the number of possible stable configurations, well, it becomes combinatorial.
So instead of string theory pointing to one unique set of physical laws,
it points to a staggering number of possibilities.
And how staggering are we talking?
The original estimates for the number of stable vacua in this landscape were on the order of 10 to the 500.
10 to the 500. That's a 1 with 500 zeros.
To put that number into perspective, it is vastly more than the number of atoms in the entire observable universe. And each one of those vacua represents a distinct universe with different physical laws. More recent analyses still point to figures like 10 to the 272,000.
So the original dream of a unique theory of everything just shattered.
It was instantly shattered and replaced by the reality of a multiverse of, well, near infinite diversity.
This brings us directly to what critics call the falsifiability crisis. If your theory allows for 10 to the 500 universes, it can accommodate almost any observation we make. Right, you just point to the right corner of the landscape.
That is the core philosophical critique. Critics like Peter Voigt argue that this structural lack of predictability makes string theory scientifically vacuous. His point is that the simple, elegant versions of string theory disagreed with experiment, and that forced theorists into these hyper-complex, non-unique compactifications that just lose all predictive power.
If a theory explains everything, it explains nothing specific.
That's the argument.
So, how does the string theory community even begin to mount a defense against this profound crisis of testability?
Their primary defense is to embrace the anthropic principle. They argue that the landscape is actually a triumph because it elegantly solves the cosmological constant problem.
The puzzle of why the vacuum energy of our universe, the cosmological constant, is not zero, but is, 120 orders of magnitude smaller than our theories predict it should be.
The most famous numerical discrepancy in all of physics, yes. So instead of looking for some deep physical symmetry that forces the constant to be tiny, the anthropic view says the multiverse contains every possible value for it.
And we just happen to live in one of the rare ones where it's small enough for us to exist.
Exactly. We simply find ourselves in the tiny fraction of vacua, where the cosmological constant is small enough to allow structure galaxies, stars, and ultimately us to form. If it were much larger, the universe would have expanded too quickly for matter to ever coalesce. We are observers, and we can only exist in an environment that is compatible with observation.
This sets up that famous philosophical battle, the Smolin-Susskind debate.
It does. Leonard Susskind, a major proponent of string theory, argues that the cosmological constant is just an environmental parameter. It's like the Earth's distance from the sun. You wouldn't seek a deep law of nature to explain that specific distance. It's just selected by the need for liquid water. He sees the landscape as the only plausible solution we have.
And on the other side, Lee Smolin, a critic and an LQG proponent, says,
He says this is a direct abandonment of the core scientific method. He argues that relying on unobservable regions of a multiverse to explain local parameters is scientifically indefensible. He called it the fallacy of the inverse gambler, meaning you are trying to infer an infinite number of dice rolls just from the single observation that you rolled a 12 this one time. You can't infer a multiverse from a single observed outcome, our universe.
So it's a clash over the fundamental definition of what legitimate science even is in the absence of data.
It is. Smolin views string theory's retreat to anthropics as the hallmark of a degenerating research program, one that failed to deliver a unique, dynamically selected vacuum and instead settled for post hoc accommodation. String theory, in his view, chose mathematical consistency over empirical accountability, #3, string theory's technical siege, and the swampland pivot.
Okay, so setting aside the huge philosophical debate over falsifiability, we have to address the technical critics, the ones who are questioning if the landscape, this astronomical space of stable universes, even exists in a mathematically rigorous way.
This is the quiet internal battle being fought right now as of 2025 over the stability of the KKLT mechanism itself. Theorists are finding that the delicacy of that three-step process may be hiding fundamental instabilities.
And if the uplift mechanism fails?
The entire 10 to the 500 landscape just evaporates.
So let's detail the two major technical instability controversies that are plaguing KKLT. First, there's the singular bulk problem.
Right, so remember, that crucial stage 3 involved adding an anti-D3 brane, a source of positive energy, to lift the vacuum. The critics argue that in the original calculations, the anti-brane was treated as a simplified probe, ignoring its own gravitational influence.
Its own warping of spacetime.
Exactly. But when you fully account for its gravitational back reaction on the surrounding Calabi-Yau geometry, the calculations strongly suggest it inevitably creates a singularity in the flux fields.
So the very thing you use to create our positive energy universe inherently pokes a hole in the fabric of the extra dimensions.
That's a good way to put it. The approximations required to treat the brane as a simple object just break down. And if a singularity forms, the compactification becomes unstable and prone to decompactifying.
Meaning the extra dimensions could unravel.
They could unravel, destroying the very geometry required for a four-dimensional physics. It suggests the KKLT vacuum is an illusion built on faulty approximations.
And the second technical hurdle is related to the possibility that this uplifted vacuum could decay almost immediately.
That's the anti-brane instability, often discussed in relation to the KPV mechanism. The anti-brane has the opposite charge to the flux fields that are dissolved in that warped throat.
And opposite charges attract.
They attract. So you risk this catastrophic brane flux annihilation. If the anti-brane meets the flux, your energy source just vanishes.
And if the positive energy source vanishes, the vacuum instantly collapses back into that stable, negative energy 8s state they were trying to escape from in the first place.
Precisely. Now, KPV originally calculated that a metastable barrier existed against this decay, meaning the vacuum could be long-lived. But subsequent, more detailed analyses that include the full back reaction and quantum effects suggest that this barrier might be much lower or even non-existent.
So what's the consensus now?
The consensus among many technical specialists as of 2025 is that no rigorous, fully controlled construction of a stable de Sitter vacuum in string theory currently exists.
This is a fundamental crisis. The reason string theory is non-predictive is because it has too many solutions. But now critics are saying the mechanism that generates those solutions is mathematically unsound.
This internal pressure has forced a major intellectual pivot within the string community itself. And it's given rise to the swampland program.
I find this pivot so fascinating because it completely inverts the philosophical mission. Instead of asking what universes are possible, which was the landscape,
They're now asking what effective field theories are impossible to embed in quantum gravity. That's the swampland.
so it's like a kind of theoretical border patrol.
Exactly. The goal is to define the boundaries separating the small number of truly consistent theories, the landscape, from the infinite number of theories that look consistent at low energies but cannot be completed in string theory. They hope to shrink the viable landscape dramatically this way.
And the most shocking result to emerge from this pivot is the de Sitter conjecture. It's shocking because it threatens to rule out our own universe.
That's the key implication. The de Sitter conjecture proposes that stable de Sitter vacua-accelerating universes like ours are fundamentally incompatible with string theory. It says they lie deep in the swampland.
How does it do that?
It states that the scalar potential, the V, must always satisfy a steep gradient bound. The potential must be too steep to allow for a true, flat, stable minimum with positive energy.
Wait, if our universe has been accelerating for billions of years, and we attribute that acceleration to the cosmological constant, which is a true positive vacuum energy, what does this conjecture imply about dark energy?
It implies that dark energy cannot be a true cosmological constant, lambda. If the potential must have a steep gradient, then dark energy must instead be a dynamical field.
The field that's rolling.
A quintessence field, yes, that is slowly rolling down that steep potential. And this rolling implies that the acceleration we observe is temporary and will eventually change or end. If the swampland conjecture holds, it doesn't just invalidate KKLT, it forces a dramatic revision of the standard model of cosmology.
So string theory is fighting a multi-front war. It's got technical instability, a philosophical abandonment of predictability, and now a self-inflicted strategic pivot that threatens to rule out the basic physics of the universe we actually observe.
That is truly high stakes.
It is. So now let's turn to the other contender, loop quantum gravity, which faces really the opposite kind of problem. Not too many solutions, but a massive struggle to define a coherent, continuous dynamics.
LQG is built on this idea of conceptual purity. It's centered on the principle of background independence.
Which comes straight from Einstein.
Straight from general relativity. GR taught us that gravity is the geometry of spacetime. It's not a force moving through a fixed space, it is the shape of space. So, LQG argues, we must quantize the geometry itself. Treat it as the dynamic variable, not as a fixed stage for physics to play out on.
Which is string theory's approach.
It is.
So if they're so committed to background independence, how do they build a quantum theory of space without assuming the continuous metric that we normally use?
This is where LQG achieves its greatest triumph. In its kinematics, which is the description of the states of quantum space, they achieved a rigorous, non-perturbative quantization by rewriting GR using a specialized set of variables.
Ashtekar variables.
Ashtekar variables, yes. They look a lot like the variables used for other successful quantum field theories, and that was the key.
And the result of this rigorous quantization is a fundamental granularity. Space is woven, not smooth.
Absolutely. The quantum states of space are described by these things called spin networks. They're essentially graphs made up of nodes and links.
So you should think of space not as a smooth fabric, but more like a finely woven piece of chainmail.
That's a great analogy. The links in the chainmail carry half-integer numbers, or spins, and these represent discrete quanta of area. The nodes, where the links connect, they carry intertwiners, which represent discrete quanta of volume.
So space isn't continuous, it's atomic, fundamentally, at the Planck scale. And unlike string theory, LQG gives a quantitative prediction for this discreteness.
It does. The spectrum of the area operator is defined by a specific precise formula, and what this formula does is guarantee that both area and volume have a smallest possible non-zero size.
And this discreteness is what solves the infinity problem.
Critically, yes. It acts as a natural ultraviolet cutoff. It regulates those catastrophic infinities that crush classical particle gravity. It solved that problem without needing any extra dimensions or new symmetries.
That is the triumph of LQG, a rigorous quantum structure for space itself. But you mentioned that while kinematics is the triumph, dynamics is the tragedy. What's stopping these spin networks from evolving in a physically meaningful way?
The issue lies in defining the Hamiltonian constraint, which is written as h hat. This constraint is the core dynamical equation of the theory. It's what dictates how the spin networks evolve over time.
And in quantum mechanics, you have to solve this equation to find the physical states.
Right. You have to solve h hat applied to psi equals 0 to find the physical, timeless states of the universe. The problem is that the classical expression for this Hamiltonian involves nonlinear curvature terms.
And trying to map nonlinear curvature onto a discrete quantized graph sounds, well, impossible.
It's ill-defined, so theorists have to regularize the constraint. They express the curvature in terms of holonomies or Wilson loops, which are traced around small paths on this discrete graph. And this necessary step is what introduces the ambiguity crisis.
So string theory had too many physical universes. LQG has an infinite number of ways to define the single equation that governs physics.
That's exactly it. The ambiguity problem stems from this regularization process. Since the quantum graph is discrete, you can't shrink the loop you're using to define curvature down to zero area. So your choice of which loop to use, your choice of representation, the precise topological routing of the arcs you add to the graph.
You can do it in a potentially infinite number of ways.
You can. And each choice is mathematically consistent, but each choice defines a fundamentally different physics. It's a landscape of Hamiltonians.
That really undermines the very predictivity that LQG champions over string theory. If you can't select a unique dynamics, how can you claim to describe the unique reality we live in?
And while some consistent anomaly-free operators have been proposed, critics argue they're completely ad hoc. There's no physical guiding principle within the theory to select the correct dynamics.
And what's more, the resulting operator is often described as ultra-local.
Right. Critics suggest that to achieve mathematical consistency, the operator ends up acting only on individual nodes of the spin network. It doesn't successfully propagate degrees of freedom across the graph.
If it's ultra-local, it means that quantum geometry can't talk to itself effectively over a distance. And if it can't talk over a distance, it can't generate the long-range force of gravity we need.
Which leads us directly to the critical test, the classical limit. LQG has to demonstrate that its discrete spin networks coarse grain. That means when you zoom out to large quantum numbers, they have to perfectly reproduce the smooth, metric-based general relativity we observe.
This is often called the graviton propagator problem.
And it is the single toughest challenge. In standard physics, the gravitational interaction between two masses is mediated by a graviton, and its influence falls off as 1 over r squared.
But LQG doesn't have an r.
LQG has no fixed background metric to even define the distance r or the concept of propagation, so recovering this smooth classical behavior is exceptionally difficult.
Has there been any breakthrough in showing this coarse graining?
There has been partial success, mainly through the spin foam formalism, which is the path integral, or spacetime history, version of LQG. Carlo Rovelli and his collaborators show that the asymptotic large skin behavior of the vertex amplitude can mimic the graviton propagator.
That sounds like they found the graviton.
Well, there are huge caveats, unfortunately. That result relies on examining the large spin limit of single, simple triangulations of spacetime. It is not at all clear that if you sum over the infinite possible histories of spin foams, the full path integral, that the smooth graviton behavior is preserved.
So it works in a simplified case, but maybe not for the full theory.
And many spin foam models are plagued by their own divergence issues, or they're dominated by flat geometries that don't look anything like the curved classical solutions of GR. This leads to the infamous dustification critique.
Dustification, that's a very strong visual. What does it imply?
Critics argue that the LQG quantization procedure pulverizes the differentiable structure of spacetime. They claim that the resulting phase space, the set of all possible geometric configurations, doesn't yield Einstein gravity in the classical limit.
It yields what?
A disordered polymer phase, a collection of weakly linked disconnected points like dust, rather than a coherent curved manifold.
So the very attempt to ensure background independence, the core philosophical strength of LQG, might ironically destroy the mathematical foundation needed to recover the smooth gravity we see every day.
It's a profound dilemma, and we haven't even mentioned the distinction between time signatures. Early LQG models used mathematically simpler Euclidean gravity with 4 spatial dimensions. But our universe is intrinsically Lorentzian.
3 + 1 dimensions, which accounts for the difference between space and time.
Yes. And switching to Lorentzian models, while conceptually necessary, introduced severe new technical hurdles. You get divergences in the path integral amplitudes, making the connection to physical reality very tentative. The struggle is proving that this inherently discrete framework can consistently handle the dynamic, time-dependent nature of our Lorentzian universe.
So with both theories facing this deep theoretical gridlock string theory crippled by too many solutions, LQG trapped in kinematics, The only way out is through experiment. What empirical evidence have we found so far?
Let's start with loop quantum gravity's most tantalizing phenomenological signature, loop quantum cosmology, or LQC.
This is where they apply LQG principles to the simplified geometry of the entire universe.
Exactly. And LQC famously resolves the singularity at the beginning of time. Instead of the infinite density of the Big Bang, LQC predicts a big bounce.
A bounce from a previous contracting phase of the universe.
Precisely. The math shows that when the universe contracts and reaches Planck density, these repulsive quantum geometric forces, which stem directly from that granular structure of space, kick in and cause the universe to rebound.
And this was touted as a potential quantum gravity smoking gun, right?
It was. LQC proponents were thrilled because they claimed the pre-inflationary dynamics of this bounce could leave specific observable signatures in the cosmic microwave background. Things like power suppression at large scales.
But this claim has recently faced a major, very detailed critique, the cosmic tangle critique from 2024-2025.
And it is a devastating technical challenge. The critique suggests that the LQC predictions are just artifacts of unjustified approximations, not fundamental physics.
Where did they go wrong?
The issue is that LQC relies on effective equations, classical equations with small quantum corrections, to track how perturbations travel through the bounce phase.
But the critique found those effective equations were mathematically invalid right where you need them most.
Exactly. The analysis showed that these effective equations break down at densities as low as half of Planck density. That means the entire calculation of the bounce and the propagation of perturbations occurs in a mathematically invalid, uncontrolled regime.
And assumptions they made about higher order corrections were wrong.
They were false. The corrections are large, and they could potentially wash out the predicted signal entirely. It goes back to LQG's fundamental problem with continuity.
How so?
The critique also highlighted the difficulty of even defining perturbations on a discrete quantum background. There are no-go theorems suggesting that LQG's discrete area spectra are incompatible with a covariant line element, which is what you need to define a smooth background metric for the perturbations to propagate on.
So the predictions might just be artifacts of the coordinates they chose.
They may be gauge artifacts, yes, not verifiable physical reality. It leaves LQC, for now, without any verified phenomenological support.
Okay, let's pivot to a different empirical signature of LQG's granularity. Lorentz invariance violation, or LIV.
This is the classic, most testable signature. The idea is that if space is atomic, that structure should act like a crystal lattice, and it should subtly affect high-energy particles traveling through it.
It would make the speed of light slightly energy dependent.
Right. High-energy photons should experience a tiny time delay compared to low-energy photons when they travel over cosmic distances.
And astronomers have the perfect test beds for this. Distant gamma ray bursts, or GRBs.
Yes, objects like GRB 090510 or that incredibly powerful record-breaking GRB 221009A. They send photons of wildly different energies across billions of light years. Even the slightest speed variation should accumulate into a measurable time difference when they arrive here.
And the result?
Zero time delay has been found. The constraints are incredibly severe. They rule out simple linear Lorentz violations up to energy scales that are significantly beyond the Planck mass itself.
That feels like a near fatal blow to the simplest, most promising phenomenology of loop quantum gravity. If space were a simple crystal lattice, we should have seen the effect.
We should have. It forces proponents into more defensive, highly complex modifications like deformed special relativity, DSR, but that's a retreat necessitated by a null result, not a positive prediction from the theory score.
All right, now let's look at string theory's big empirical hope for decades. Supersymmetry, or SUI?
String theory, in its most consistent versions, relies on supersymmetry. The primary low-energy prediction was that every particle in the standard model, the electron, the quarks, the photons, should have a heavier superpartner, a selectron, a squark, a photino, and so on.
And finding these partners would have been the first direct evidence for the framework.
The ultimate testing ground was, of course, the Large Hadron Collider, the LHC.
Yeah.
We found the Higgs boson, which completed the standard model, but we found zero evidence for superpartners. The LHC has systematically pushed the exclusion limits, confirming that if superpartners exist, their masses must be far into the multi-TeV range.
Now, this doesn't strictly falsify string theory, does it?
Yeah.
You can always just push the energy where SUTY breaks higher and higher.
You can, but it ruins its most compelling natural feature. Y was initially so popular because it naturally solved the hierarchy problem, the question of why the Higgs boson's mass is so small compared to the Planck mass.
But if the superpartner masses are incredibly high, that naturalness just vanishes.
It completely vanishes. And this pushes string theorists further back toward relying on anthropic reasoning, suggesting we just have to live in a vacuum where Caesarea happens to be broken at a very high, unnatural scale. It severs its most direct and promising link to reality, ###Z, the sociological dimension, and the great stalemate. The scientific intractability of quantum gravity has, naturally spilled over into this bitter ideological and sociological conflict. It's widely termed the string wars.
It really highlights the tension between pursuing mathematical beauty and the fundamental demand for empirical verification.
It does. And critics like Lee Smolin and Peter Voigt have argued strenuously that string theory achieved a near monopoly on academic resources, funding, hiring, tenure slots, despite decades of failure to match experiment.
They argue that this structure created a culture of groupthink.
Yes, where young, talented theorists feel pressured to work on strings to ensure their academic survival. And this leads to the marginalization of rigorous background independent alternatives like LQG. Voigt, in particular, argues that the community has been forced to redefine the standards of scientific evidence, favoring ideas like non-empirical theory confirmation just to justify the continued research.
Yeah, this tension was really crystallized in that high-profile Gross-Ravelli debate in 2021.
It was. You had David Gross, a Nobel laureate and a central figure in string theory, versus Carlo Rovelli, one of the founders of LQG.
What was Gross's main argument?
His core argument was that string theory shouldn't be viewed so narrowly as just a predictive theory, but as a vast framework, something analogous to quantum field theory itself.
He emphasized the deep mathematical insights it's given us.
Absolutely. Breakthroughs like the ADA-CFT correspondence, the idea of holography, which equates a theory of gravity in one dimension with a quantum field theory in one fewer dimension. He dismissed LQG as, aesthetically unappealing and ultimately unsuccessful.
And Rovelli's counter was to focus on string theory's failure to meet its own stated goals.
Exactly. Rovelli pointed out that string theory promised a unique, finite theory of everything, and instead it delivered an infinite, non-predictive landscape. He argued that LQG's modesty, focusing only on quantizing gravity itself, was a virtue.
And he positioned LQG's commitment to background independence as the true Einsteinian lesson.
The lesson that string theory refuses to embrace because it relies on a fixed, high-dimensional background metric.
So if we step back and just look at the state of the art in 2025, we are in a profound mutual stalemate.
The stalemate is crippling. It's crippling because each theory is flawed in the opposite way, and neither has managed to cross that critical threshold of predictability and verification.
Let's summarize. String theory is?
String theory is a majestic, complex edifice. It revolutionized mathematics. It cured perturbative gravity's infinities. But it's non-predictive, it's technically unstable in its de Sitter realization, and it's cornered by its own swampland program. It's a theory of everything that functionally predicts anything.
And LQG?
LQG is rigorous. It successfully quantized geometry, it upheld the background independence principle, and it provided a precise, discrete structure for space. But it's trapped in kinematics. It can't overcome the ambiguity crisis to define a convincing dynamical model, and it fails the critical classical limit test to recover smooth GR. And its most promising phenomenological signals have been discredited or ruled out.
It sounds like the era of rigid strings versus loops dogma might just be ending out of collective exhaustion.
That is the hope for the future. The realization may be setting in that neither camp alone holds the key.
The frontier is shifting.
It's visibly shifting towards synthesis and compromise. You see this in the Swampland program, where theorists are ironically using constraints championed by LQG critics to narrow string theory's possibilities. You also see a movement toward holographic approaches applied in a background-independent way, borrowing tools from string theory but integrating them with the foundational insights of LQG.
So the final resolution might require abandoning the rigid dogmas of both camps.
And accepting a third path that fundamentally alters what we even assume about reality. #7, outro and provocative thought.
It's just astonishing to realize that after a century of intense work, the two leading approaches to quantum gravity are paralyzed by these mutually exclusive problems. String theory has too many possible universes.
And loop quantum gravity has a beautiful start, but can't generate the continuous dynamics necessary to connect to our universe.
The ultimate choice between them seems to reflect a much deeper philosophical choice about what physics even is.
It does. Are we willing to abandon predictability and strict empirical falsifiability in favor of ultimate mathematical unification? That's the string theory choice. Or are we willing to abandon the smoothness of space-time and the very concept of continuous distance in favor of maintaining the purity of background independence? That's the LQG choice.
And what if that initial framing of the choice, either continuity or discreteness, is the fundamental error?
That is the provocative thought we want to leave you with. These theories clash, but they share deep foundational assumptions. And one of the most critical is the definition of time.
Both of them struggle with time.
Tremendously. General relativity suggests time is relative and dynamic, while quantum mechanics requires a fixed external measure of time for evolution to happen. They are in direct conflict. So what if the key to unlocking quantum gravity demands that we surrender the very definition of time itself before we can unify space, matter, and quantum reality?
What if the universe is fundamentally timeless at the Planck scale?
That is something truly worth mulling over.
A magnificent, unfinished symphony indeed. Thank you for joining us on this incredibly deep dive into the very fabric of reality. We'll see you next time.